pleasure of Mohammed Abouzaid from Stanford. Mohammed is a receiver of New Horizon Prize in 2016, and he was my ICM speaker in 2014. He's going to talk about 100 years of Morse theory.
Thank you. It's a pleasure to be back here. So, 2 or 3 years ago, I noticed that it was close to being 100 years of Morse theory, and I didn't do something very active, but I just tried to tell this to people, or maybe there would be some activity around it. And then I heard nothing, but apparently they did notice. So TNG's apparently just gave a talk earlier this fall with, I think, the same title. So that's great. This is, of course, going to be my version of 100 years of Morse theory, so as people may guess, it's going to be Morse theory is going to turn into Floer theory at some point. But anyway. This is Morse's address to the AMS in December 2023, so from some point of view, it's a little bit more than 100 years. It's kind of interesting, so he discusses that he was given a real analytic function with n variables. Birkhoff has shown that if you make some assumptions about the number of critical points, there are too many minima, then there are other critical points in addition. That's what he did this in 2023. Yeah. Yeah. Sorry, 1923. I'm sorry.
Oh, okay. It just took a long time to get published.
Yeah. So anyway, as I say, if you have a function with too many minima, then there have to be extra critical points. So apparently, very complex. And then Morse kind of started building a theory around this. And then the paper didn't come out until 1925, so I'm going to say 2000 again. And this is the paper. Relation to the critical points of a real function of n independent theory. It's actually very interesting because already in this paper, I don't see where it is, maybe it's not in this part, he realizes that you don't really need real analyticity anymore. Actually, it's right here. Let f be a real function defined as continuous in R and B. So let's say continuous third-order partial derivatives. So in between the time that he gave the talk and the time that he wrote the paper, he realized that you don't need to be real analytic. You don't need basically. And so in this paper, he kind of did what we now think of as finite dimensional Morse theory, and I will say more about it later for people who have never seen this. What I do want to say is that between these two papers, he gave another AMS address about what we now think of as infinite dimensional Morse theory, which is the study of geodesics. So he noticed extremely quickly that you went extremely quickly between the finite dimensional and the study of geodesics, and then the next paper, I think, was written in 27. So we have like 2 more years in which we can claim 100 years Morse theory, depending on where we count.
That would be better downward direction.
Absolutely.
Absolutely.
Yes.
So it's sort of the same.
It's sort of the same, but you have to realize that you can make this jump, and I think it's, of course, a huge conceptual jump. But yes, technically, it turned out not to be too different, but you have to realize that. Okay, so keep going the wrong way. Okay, so let me now give some mathematics as to what's going on. So, in some more modern language, because it can be a bit hard to decode how Morse goes like this. So he took a compact codimension zero-sum manifold of Rn, okay, and with boundary. And then he considered the function. And he assumes the gradient vector field of this function points outwards. So of course this means in particular he's not thinking about Riemannian geometry. He's usually just uses just standard metric on Rn, restricted to the subset. And then he makes this assumption that is now standard, which is that the function has non-degenerate critical points. This is exactly this thing that we teach in multivariable calculus, or maybe even first single variable calculus. You have a function, you look at the critical points, you look, okay, generically the second derivative, when the derivative vanishes, the second derivative doesn't vanish, and this is, that's this condition, that's this non-degenerate. And then he was interested in these two kinds of numbers that appear. The first is the number of mi, using his terminology, of critical points of index I. Okay. which means basically you have a non-degenerate critical point, which means you have a Hessian, it's a positive, it's a symmetric matrix. And then you use some kind of classification. And over the real, the classification is roughly speaking that you have the negative definite subspace and the positive definite subspace, and you record the dimension of each of them. And index I is the dimension of the negative definite subspace. So that's one collection of numbers. And the other collection of numbers is the integral Betti numbers. Okay? So this, of course, was at the time where the definition of homology was just being crystallized. I looked at some point in Veblen's book, which precedes Morse's work, and there you can see that he's just at the cusp of realizing that you can define homology with coefficients in the abelian group that are not the free abelian group, but it's not clear. It's never very clear exactly what are the coefficients. So here I'm quite, for Morse, it's pretty clear we're doing integral homology. Coefficients. Okay, so we have these two collections of numbers, and then because it's, I feel like it's appropriate to do here. Okay, this is in case you don't know what the Betti numbers are. So I assume at Stony Brook everybody knows what the departments of geometry and topology. But in case somebody doesn't know, okay. So the number R1, if on the plane, is just one less than the number of boundary components. Remember, everything is a subset of the plane. But for R3, there's two kinds of holes you can put. There's a kind of holes where you just literally you just have something filled with jelly inside, and that's one kind of hole. And then there's also the holes which forms like the genus boundary, which you can see on the boundary as giving you genus. Okay, so that's R1 and R2, these two types of holes. And of course, in higher dimensions, there are different types. Okay, so now comes the main result. This is Morse's main theorem in this paper. It says, okay, if you under boundary conditions, basically, if you fix this conditions that I said earlier about this compact manifold of boundary and this function with gradients as outward pointing, then the numbers Mi and Rj are related as follows. Okay, and it's a very complicated relationship, and the beginning is very simple. This first one says there must be at least one minimum. Okay, so if it's connected, there must be at least one minimum, and if there are R0 components, then you must have at least that many. Point. And the next one is it's what this interpretation of what I was saying at the beginning. If there are more minima than are required by the topology, okay, so that's this one here. So if that's this, if there's more of them here, then there must be some index 1 critical points. Again, assuming that there's each one. There's the index 1 critical point that kind of cancel them together, and then things keep continue. Formulas become more complicated. Okay, so this is the if you the standard reference from when I was a graduate student. Well, it was not this paper. I did not read this paper as a graduate student. I read Miller's book, and of course this is explained in a slightly less computational way, which is what I'm going to explain next. Okay. Any questions before I move on? Okay, so, so this was 1920s, then topology developed very quickly after World War II, and a lot of these things were summarized in this book, and you could say at that point that the main all of Morse theory was more or less formulated in this package here. So we get rid of boundary because now we can work with abstract manifolds. Okay, so why think about things with boundary? You can do it with boundary, it's more complicated. You take a smooth compact manifold. You take a function, which is Morse. Again, that just means the same thing, non-degenerate critical points. Then what was proved essentially in Morse's book is that M, manifold M, is homogeneously equivalent to some kind of cell complex. And in this cell complex, you can build it. The cells are indexed by the critical point. So there is a cell of dimension I for each critical point in index I. Okay? So that tells you that the level of the homology type, you can build the manifold from the Morse function. And if you apply to this formulation here the machinery of homology and exact sequences, long exact sequences on homology for pairs, then you recover. You can recover everything that Morse stated explicitly. So that was kind of the way things were viewed in I would say in the 60s. There's one thing. Dennis can correct me if I say something wrong. I'm sure he'll not. If a good summary of how things were viewed in this era is given in Bott's paper from 1988. And the reason I wanted to kind of point that out is because in Bott's paper, he exactly is saying, okay, this is how we did this back when I was a young person, and now in the early 80s there is a new point of view. Okay, and it's this new point of view that I will be most of the next 10 minutes of my talk before I jump onto Floer homology and Floer homotopy or something. Okay, so what is this new point of view? So this new point of view is sometimes called, well, these days we often call it the Morse complex. Typically, for just naming something not for the person who invented it. It's actually extremely hard to pin down who first defined it. The first definition in the literature is in Floer's work. Witten's paper doesn't. It's usually credited to Witten. Pardon?
Witten.
To Witten. So Bott credits it to Witten somehow. This definition of this Morse complex is credited by Bott to Witten, but Witten never wrote anything down. He wrote something about Morse theory, but what's written is not. What he wrote is not the Morse complex. So I think what Bott says is that Witten explained this to him in his office or something. No reason to doubt Bott. But okay, so now instead of somehow we kind of lose information. Instead of saying something about the homotopy type of the manifold is given by some cell complex, or something really at the level of topological spaces, so we can indexed by manifolds, which is passed to homology. Okay? So, given a function f on manifold, which can make Riemannian. Why am I making Riemannian? So that I can make sense of gradient flow. You don't need it to be Riemannian. As long as it's smooth, then you can take a notion of gradient line. Okay? And the function will determine the chain complex. Chain complex, we call it the Cn. I don't know how this became standard, because this is like a French thing, like whatever, chains of Morse. Like Morse chains, but anyway, this is how we write it. The Morse chains of F, which is freely generated by the critical points. And when you take this chain complex and you compute the homology, you get ordinary homology. Okay? I will explain, I will say something concrete about it in the next few slides. So what is this, the genericity condition? Okay? This genericity condition is exactly about this negative, about the behavior of these negative and positive definite subspaces of the Hessian under the gradient flow. So just to draw some pictures here for people who have never seen them, because before I just learned algebra. So this is at a maximum. You look at all the directions. The negative definite subspace of the Hessian is everything. And so you just flow down, and at minimum it's nothing, everything flows in, and at a saddle point there's one arc going in and one arc going out. Okay? So the condition that Smale formulated, which is why this is called the Morse-Smale condition, is that the things that come out of the critical point and things that come up from another critical point, they meet transversely. Keep going the wrong way. Okay, so how do we define this chain complex, or how did Floer define this chain complex? I should really say. So as I said, so we're gonna this chain complex. Well, the chain complex has generators of each degree. In this setting, there will only be generators of degree between 0 and the dimension of the manifold. Nothing below, nothing above. And the ones of degree I are exactly the ones of index I. I've already explained what the index is. And so we just need to construct this operator: ei minus 1, ei minus 1, so on and so forth. Okay. And the definition of a chain complex, I assume again everybody knows what it is, but I'm going to write it anyway, is that when you go twice, you get 0. Okay? And then when I said earlier that the homology, what that means is that the quotient of the kernel by the image is going to be the homology. Okay? So this di I minus 1, for example, it's just a big matrix. Okay? It's a big matrix, and it has some coefficients. The coefficients, so just even coefficients are numbers. Okay, what kind of numbers is a good question. We'll come back to that later. So over here you have the index I critical points, and here you have the index I minus 1 points. And so for every pair x and y, I need a number. Okay? And the realization is that this number, so the kind of Floer's observation, which again, apparently Witten knew already, is that we can set this up so that the number is exactly the number of gradient trajectories, so which means the number of solutions to an ODE, where this ODE is defined on R, and the solution goes to x as you go to minus infinity, and y as you go to plus infinity. You just count how many solutions there are. Okay? So there's a different way of thinking about this, which is that you take the intersections of the ascending and descending manifolds of x and y. The fact that the index difference is 1 will tell you that this is a one-dimensional manifold, and you count the number of components, but you do it with signs. Okay? But that's the definition of this chain. And as I explained here, these are the two ways of describing it. So one way is an intersection problem, and the other way is the solutions in this ODE, which is the gradient. That's why it's called the gradient solution, for paths which limit to x. Okay? And so you count this thing, and then you would like to prove, so you count the defined by the matrix, and then you'd like to prove what I wrote earlier, which is that the composition, the product of these two matrices is 0. And again, I assume many people have seen this before, but it's kind of a nice thing to repeat because it's an interesting place where topology enters some setting where you wouldn't expect. So, what does it mean to say that this composition is 0? Well, let's write dxy for the coefficient that we see here. Okay? So I'm trying to prove that given x and z, the sum over all y, dxy times dyz is 0. Okay? And this sum is the same as saying, is basically the union over, is basically counting the number of elements of this set. So xy, so this m is the number of gradient solutions that go from x to y, y to z. So this is some zero-dimensional manifold. And the first thing that, as an undergraduate, I learned when probably the first real math book I read was probably Milner's book on differential topology, and the main thing that's proved there is that this is exactly the condition for the zero-dimensional manifold being the boundary of a one-dimensional manifold. Okay? That's the main thing. It's a very simple thing to say, but that's somehow some fundamental statement of topology. So now we reverse it. The way to prove this is to exhibit a one-dimensional manifold whose boundary is this, and that is exactly the moduli space x, gradient trajectories from x to z. More precisely, some kind of compactification of it, where instead of just taking flow lines from x to z, I allow myself to stop at y and continue. Okay? So this is called the moduli space of a broken trajectory. Instead of a direct trajectory from x to z, we go take a trajectory from x to y and y to z, and then there is you can either do it from the point of view of a topologist, in the soft way, or we can do it from the point of view of an analyst, of trying to understand if I had a trajectory that goes from x to y and one from y to z, can I produce one nearby by some implicit function theorem which would go without stopping? And that indeed can be done. And that's basically the proof. And once you've done that, you've proven that this compactification exists and it has the correct projection. Okay? So that's the definition of Morse homology. And it's been very useful, and of course I personally use it every day when I do Floer homology, this infinite dimensional setting. I'm not going to say too much about that. But what's interesting is that, the statement that I made here only involves zero and one-dimensional manifolds. And it's very natural to wonder what happens if you use higher dimensional if you use the moduli spaces, which have higher dimensions. Okay? And this is exactly what Floer did. Okay? So this paper was written basically, the same time that Bott was writing his paper about Morse theory and where Morse theory is going. But of course, he didn't quite see that this is one direction that Morse theory is going, because Floer had not quite made this statement as explicit. Not many people had understood what Floer was trying to say. So So first of all, I would like to say, and I read this paper as a graduate student, but I completely missed this part. Like, I just had no idea it was there. At some point, a couple of years ago, I was giving some talks, and then Tom Rofka came to me and said, you really should credit Floer for the formulation of Floer homotopy, and if you look at his paper, this one, you will find it. And so I looked at it, it's not in the introduction, just keep turning the page. It's really hidden somewhere in the middle. It's impossible to find. Well, apparently it's on page 215. Okay, it's literally in the middle of the paper. So what does Floer say? So Floer says, okay, now let's think about these moduli spaces and think of them at the higher dimensional ones. Okay? And then his point is
of the trajectories
that go between critical points.
Index 3 or
Yes, different 3, 4, 5, 6,
so the
all of
dimension is 3 minus 1.
A dimension is index x minus index y. Okay, so I'm sorry, it's a little bit small. I'm going to still try to read it. So he says, the way we're going to use it is as follows. We're going to extend this program of defining Morse theory, which is Morse homology. We're going to look at a general cohomology theory, and we want to compute the cohomology of I of S. That's basically the cohomology of the manifold. Let's just say that's what we're interested in. We're going to compute the cohomology of the manifold in a way that's similar to the above, in a way similar to how we did for ordinary homology. And we're going to do it as follows. Okay, this is pretty funny because it tells you that Floer, probably hadn't talked to too many algebraic topologists, because this is just wrong. We're going to have a chain complex, and with our chain complex, it'll be a direct sum over all the critical points of the homology of a point, okay, shifted by the index, which is basically the reduced homology, the generalized homology of the sphere. Okay? If you don't know generalized homology, just ignore it, just think like Bordism, and I will say more about Bordism. Okay, and then there's going to be a delta homomorphism, which is basically the differential. And instead of just counting things which are zero-dimensional, it will depend on trajectories of arbitrary dimension. Okay, and then he gives an example. If you did the homotopy, then this is how you would do it. Okay, and the point is that this doesn't work. I think maybe Dennis may be the first person to point me to a paper from the 60s that basically explains that if you have a homology theory that is computed naturally by a chain complex, then it's just a direct sum of shifts of ordinary cohomology. Okay? Nothing, you can't see anything. What the correct version of what Floer should have said, not that I blame him, is that there would be a spectral sequence. There would be a version of the T-Hertzberg spectral sequence, and this would be the first page of it, and then you would kind of do something. Eventually you would hope that it would converge to the right answer. But nonetheless, this is clearly the right idea. And what I want to talk about for the next half hour or so is kind of how we now know how to implement this in very usefully. Okay, any questions?
Sorry,
Yes, absolutely.
just about in, I don't know if it's the same case that I've written, but there's something where you form the differential using Morse function and all the information you concentrate at critical points.
Yeah,
How does
so
that?
that's the other paper by Witten. This is by Floer.
I see. So this paper by Floer is inspired by that paper of Witten, or
So let me say, so Witten's paper is basically about how to think about the Rabi cohomology from the point of view of Morse theory. That's really what it's about. And so indeed, that's why Floer's paper refers to Witten's complex. So these things are a little bit, it's very, completely clear. I mean, I was not around at the time, or I was alive, but not going back. So I can't give I can't say much more than that. But it's obvious that Floer was influenced by Witten.
Okay. And this idea of deforming differential, does that appear in Floer's work?
I would say in Floer's work, he was really already thinking about symplectic manifolds, and then like there's deformation of the differential coming from pseudo-homomorphic curves and so on and so forth. So anyway, this Floer's work, he doesn't use this kind of like flowing the differential along the gradient flow. That doesn't appear too much. Okay. So this is some idea, and then the question is to make it precise. So there's this word of generalized homology theory that appeared. I do not want to define it. So I have this point of view that, unless one's living is made computing homotopy groups, there are only two homology theories that you need to know about other than ordinary homology, Bordism and K-theory. And all the other ones are just manufactured so that people can compute these things. Okay? So let's talk about Bordism. So Bordism is probably the homology theory that Poincaré would have wanted to define if he had the language to do it. So instead of adding cycles, the way you just take the images, you add cycles by taking the disjoint unions into domains and remembering the map to the target. Okay? So one cycles are just closed one manifolds with a map. You add them by taking union to one manifolds. Now you would like to make sure that your cycles are not decomposed into disjoint unions of the number of their components. So you add some relation that says this one cycle here, these two one cycles, are boarded because they are the common boundary of the two-dimensional manifold. Okay? So you start with the intuition of cycles, and you try to make it precise. Make it precise as manifolds with map to the target. You realize you need an equivalence relation, that the most natural equivalence relation is, again, coming from manifolds. Okay? And this, in higher dimensions, gives rise to the Bordism groups. So this symbol, omega, was used by Milner to refer to oriented Bordism. And somehow we just now use it for everything else. So omega means I look at compact manifolds with some choice of orientation. Sometimes you say no orientation, that's okay. It's generated by compact manifolds of dimension n, mapping to the target. And then there's relations coming to the boundaries of n+1 dimensional manifolds. There's many flavors. Unoriented Bordism is the one that's easiest to say some things about because you don't have to write any comments about the tangent space. Oriented Bordism means you keep track of plus or minus. Complex Bordism is the one that I spend most of my time thinking about, and I think in this lecture I say almost nothing about it, and if people want some comments I can say something later. And framed Bordism is the one where you assume that the tangent space is not quite trivial, but trivial up to adding some vector, just stabilizing. And that frame Bordism is in some sense algebraically the most important theory because it turns out to be initial. The most amount of structure you can put on the tangent space. That's it will appear later. Okay, so now comes the first piece of information, which is probably new or to you most people will talk about this. So, and this is a definition that due to Cohen, Jones, and Siegel. So what did they try to do? They took the proposal of Floer and tried to make some precise mathematics out of it. And none of these, they're basically all three of them were topologists, and they were not that familiar with Floer's techniques, especially with Floer's techniques for studying pseudo-homomorphic curves in symplectic manifold or for doing gauge theory. So they were not that, they weren't going to be focused on the kind of applications to geometric questions. They tried to step back and formulate some notion that would be more abstract, from which they could try to extract these invariants. And this formulation is basically the subject of the rest of this talk. So a flow category is the structure you get when you study Morse theory. Okay? When do I mean by that? Okay? So it's a category. Okay, it's actually a non-unital category, but let's not worry about that. And in Morse theory, the objects of this category are the critical points. Okay? So you just say, I'm going to think of these moduli spaces x and y, and you can already, of course it's very natural, the moduli spaces are some kind of flow lines from X to Y. So you can just say it's a space of errors. Okay? They're the morphisms of a category. And this notion of concatenation of gradient trajectories that I showed earlier, I can think of it as a composition. Okay? Though it's, there are probably not too many people who do category theory for a living in this audience. It's very standard in algebraic topology or homology theory or category theory to say, let's look at categories enriched in topological spaces, which means let's look at categories where the set of arrows is itself a topological space. Okay? And this would be an example. But if you said that, you would not actually distill the key feature that's going to make it possible to define Morse homology or do these generalizations later. The key feature is the morphism spaces are not just topological spaces, they are compact manifolds with corners. Okay? And even that is not the main thing. Is that their could-I-mention one boundary strata are given by these inclusions. So let me write something more. So again, the statement is M and C, and as I wrote over there, so this is a manifold of dimension index, but I don't want to say this. Okay, so this part of the index, that's not part of the abstract definition. Okay, but in practice, index of X minus index Z minus 1, okay, but it's with corners, and it's so compactness, of course, is essential because if you don't have compactness, you cannot count. If you don't have compactness, you cannot make sense of the Lordism class. Things can escape to infinity, and then everything is lost. Okay. And then I said there's these composition maps, what I wrote over here. But the main thing to say is it's a manifold with corners, which means there are some codimension one boundaries. Okay, like this. And then the statement is that these codimension one boundary strata are labeled by other critical points. And what does it mean they're labeled by the other critical points? They mean they are, such as if it's labeled by Y, then it is the diffeomorphic image of this product under this composition. And then the statements in category justice also says stuff like this composition is compatible, this concatenation is compatible with doing it multiple times and we get the same answer. Okay, so that's their definition. Okay? So they defined this notion. I think it's a great notion. And then they did something with it, which unfortunately, turned out to be a little bit too cumbersome to use in practice. Which is that they basically said, given this definition, we can imitate the definition of the Morse complex, which means we're going to have a single generator, okay, for every critical point. And now it's going to be a generator. It's going to be, to build what? You'd like to say to build a CW complex, but really to build a stable homotopy type of network. Okay. So you can have a copy of the sphere, again, in the world of stable homotopy, for each critical point, for each object, and then you're going to attach these things to each other iteratively using the moduli spaces. What does that mean? Well, there is this Pontryagin-Tom construction that allows you to say that you can think of manifolds, let's say framings, compact manifolds, with stable framing, that they correspond, let's say dimension M, to maps from xk plus n to sk, letting k go to. Okay? So this translation, which I'm not going to talk about today, is called the Pontryagin-Tom construction. The reason I don't want to talk about it today is because I want to avoid it. It's a very deep construction that involves a lot of choices. It's very, it's not obvious how you go from this to, well, from here to this is pretty easy. You take the inverse image of 0. The other way, you have to make a lot of choices. So that's their point of view. And this point of view is what's for the next 40 years almost, is what's called Floer homotopy, or maybe 30 years, called Floer homotopy. You want to take this point of view of Morse homotopy. You take these flow categories and you extract those homotopy categories. So what I wanted to talk about, the thing I wanted to talk about is that we now have a way of doing this which doesn't rely on this cellular point of view. And for example, what it gives is what is, from my point of view, a completely natural model of Morse Lordism. Okay? So we don't need to go through some very complicated machinery. We need to know what spectra are, okay, to define a more theoretic version of political group. And that then makes it possible to kind of apply it more directly to geometric problems. Okay, so that's exactly what I wrote up there. So let me remind you again that ordism of M is some theory, some group, okay, that's generated by manifolds mapping to M. Okay, compact manifolds mapping to M. And now I want to think, how can I couple this question to Morse theory? And the answer is that you can, well, first let me give you the nature of the answer, and then I'll tell you how it's produced. So what I'm going to do is I claim that you can, by doing some transverse perturbations, you can associate to such a compact manifold the following data. For each critical point, so index k, we're now going to have a compact manifold now with corners, and I'm going to use curly n y. It has a dimension n minus k. So now let me explain. How would I produce it? So the simplest way to produce it, so let me draw some picture. This is the only way to produce it. Okay, here's a torus. Here's some other manifold. And mapping to the torus. Okay? This torus I drew it so that it has a Morse function. And so there's 4 critical points. So now I'm saying, out of this n, this map, I guess I didn't get this I. Okay? I can associate to every critical point, y, to every critical point, something called n of y. And what you do is you just take y, and you look at its descending manifold. That would be good to have color. Look at its descending manifold. And then you take the fiber product. Which means you take basically the inverse image. But it's a little bit, there's some compactification going on. So you take, so this is the interior of this. Interior of this is pi inverse, pi is this projection map, of the unstable. So you have to compactify it. The same way we compactify the moduli spaces and gradient trajectories by allowing brokenness. And if you do this, you have to ask yourself, how are these things related to each other? How is the inverse and that's not where the descending manifold comes. I'm sorry. The descending manifold goes here. There, much better. So if I do this construction, okay, to y, and I do it, for example, to z, how are these constructions related to each other? And the answer is, well, okay, if I take this, and y is the inverse image of this descending manifold. So at this point, it's very close to z. The descending manifold of z is nothing. So what I see is that as we go towards z, we get a boundary point. Okay? But we get a boundary point from the left, and we get a boundary point from the right. Okay? So it's not that the boundary of this is what's associated to z, but rather what we have is what's written here. Okay? I look at n of x, okay, which is the manifold that's the inverse image of things are reversed. X, y, and z are reversed. I apologize. But I think, okay, so let's call this x. Everything is reversed. Okay, doesn't matter. I look at n of x, okay, which is inverse image of this thing, and I multiply it with the gradient, space of gradient trajectories from x to y. This is why everything is reversed. And that maps to n of y, and actually maps exactly to the opposite. That's just this picture. Again, I'm taking the inverse image of this red line, it's on n. As I approach x, clearly I get the inverse image of x, okay? But I get a copy for each way that I'm moving from y to x, which means I get a copy that's indexed by x. So this is some data, and it's the data, I call this data, the data of the flow module. I'll come back to that in a second. And now the claim is, on this data, which is some kind of abstract data associated only to this flow category that we had, to the data of the MXYs and the compositions between them, we can associate a notion of Bordism, and these data up to Bordism is the Bordism group of the manifolds. That's the question. Yes?
So we say generic map, is it you fix the dimension of n or the same dimension of m for the picture?
So no, you don't. So the idea is, again, n represents a generator of the Bordism group of m in some dimension. Yeah, but I think it's fine. Okay. And maybe there's some small mistake here with numbers. So basically, for each possible dimension, the generators of the Bordism groups are given by maps into them. Any such map can be perturbed so that it's transverse to these descending manifolds, and once it's transverse, you can do this construction. Okay? And that gives you some group, and that group is that allows you to formulate a definition, which is the definition of a flow module. Okay? And now these things have, which is exactly assignments of manifolds to all the critical points subject to this rule. Okay? And on such things, there's a notion of Bordism, and the Bordism groups of flow modules over flow category is exactly the Bordism group of. Okay, so now, okay, the last 50 minutes, I want to say how you can kind of go even further with this. Okay, so this is just what happens with one space. So I've explained how, give some idea hopefully of how if you take one manifold, one Morse function, you can abstract out of it some notion which allows you to recover the Bordism groups of the manifold from some Morse theoretic notion. But you can then just keep going. Okay? So what I mean by that is you can ask yourself, for example, if I have two Morse functions, how are the Morse complexes related? And the most natural thing to do is to say, okay, well, so the picture here is, at the top, I have the gradient flow line as a function f1. At the bottom, I have the gradient flow line as a function f2. Okay? And I can just interpolate between them by some path of vector fields. And I can now solve this ODE. The solutions to ODE, which limit to critical points at f1 up here and critical points at f2. And I look at the space of solutions. What kind of properties will the space satisfy? And the answer is, it defines some kind of structure, which you could call a line module, whatever it is. But what it is, again, is something entirely about manifold. There will be a manifold, it's called B, for each critical point of f1, each critical point of f2. They will have boundary, but its boundary will be some geometric notion. It will be, you take a flow line from x1 to y1 for the function f1, followed by a solution to this mixed problem, which we call the continuation map, going from y1 to z2. Or you can do it in the other order. So, again, I'm saying the ODE that you would naturally write down to compare Morse homologies, because this is where this ODE was first written. This ODE was first written to have an intrinsic proof that Morse theory is invariant. This ODE motivates an abstract definition, and then you can interpret this abstract definition as the notion of a map. Notion of a map between a functor, let's say, not really what it is, a functor between these categories. Okay, and you can do more. Okay, so now instead of just having one interpolation, one way going between f1 and f2, I can have a one-parameter family. And that will give me the same kind of notion, except that I will now have a Bordism. I'll have some kind of, Bordism between this B and B prime. Okay, and whenever I have Bordism, I can take equivalence classes of Bordism. Okay, and now comes the main point, which is that out of all of this, you can define a category. You can define something crazy called the category of all flow categories. Okay? So far it looks like I'm just going down some rabbit hole and doing a lot of abstract nonsense with playing around with gradient trajectories and so on. So if we want to understand what this is, maybe we should ask ourselves a very natural question, which is, what's the simplest object we could study? The simplest object we could study would be we do not have all this complication, we just have a single one object, one critical, which means Morse theory on R0. Okay. What would this give me if I were doing this? If I were studying this situation? Okay, maybe I'll skip this slide because it's a little bit too long for this audience. I'm sorry. Even though the one thing I was about, the thing is that, okay, I want to say the slide basically says something like this. The structure of this category is sufficiently rich that you can make sense of the statement that understanding this one category with one object determines everything else. So this is what I'm trying to say. You prove that the flow category is trivial if and only if morphisms from this point category vanishes. Now, the reason I really want to say this is because our initial proof was wrong, and there were two postdocs, Hegelog and Overlook, who actually pointed out the mistake and corrected it. So I was debt to pay. So that's the proof in our paper is wrong, so it'll be correct. Okay, let's do something more interesting. So now we're back to some, so I'm saying like there's some result that tells us that this is the most interesting thing that we care about, which is the thing with one object. Okay? And so it's like a situation where you have a category of modules, or there's a ring, and then you're like, what is this ring that we're computing? What is this thing that's associated to it? Okay? And now the answer is, well, if you look at this one object and you try to look at morphisms between it and itself, what you'll realize is that the morphism is exactly frame Wordism. And one of the first things that I wrote over here is there's supposed to be some relationship between frame Wordism, contrary to Thomas morphism, and homology. Okay. So what this suggests, and that is exactly what we prove, is that this category that I construct only out of manifolds with boundaries and corners, and only out of notions that are motivated by studying ODEs that show up in Morse theory, it is not some strange gadget. It's in fact the central object of algebraic topology.
Stable algebra.
Of stable algebra. Correct. It is the central object of stable algebra. It's not surprising, because the statement that the stable homotopy groups of spheres, given by Friedman was very old. It goes back to Pontryagin. Okay? But, and I just did that's more propaganda. So, again, and Tom's work was exactly about realizing, maybe Sayre just before him, that if you want to compute these geometric objects, your best shot is to formulate them in the world of homotopy theory. But then afterwards, everything was done in the world of homotopy theory, especially after Floer. All the work was done on this side, and sometimes you manage to compute something by this side, but you never formulate any structure on this side. But symplectic topology, for reasons that I won't be able to explain too much about today, symplectic topology produces a lot of things on this side. Okay? In fact, so many things on this side that sometimes we have trouble seeing how we could possibly construct the object on the other side that corresponds to it. And having a formulation of this nature tells you that you maybe don't want to do that. Maybe what you should do is you should construct all the structures, all the notions of what we say we're ring, doing algebra, doing commutative rings. You want to do it all over here. When you want to compute, you do what Tom did and realize and go back to the other side and compute. But this side is good for computation, and this side is good for structure. Okay? That's the philosophy that I want to advocate. Okay, so now I want to close with some work that is not mine. I want to say that there is this philosophy has made it possible to make advances in an area that's long been known to be one of the trickiest area, which is to try to understand how Morse theory interacts with group actions. Okay? So this is a picture of the same torus over here, except this time I made it straight. Okay? And it's obvious that it has this L2 symmetry. Okay? So this height function has the same critical points over there. Now there is a problem, which is that the descending manifold of this index 1 critical point goes into the descending manifold of this index 1 critical point. That should not happen. If you do a small perturbation, you can get rid of this, but you cannot do it by a perturbation that keeps the symmetry. the symmetry, if you keep the symmetry and you don't create more critical points, you keep just the number of critical points, there will always be a gradient flow line that should not be there. It goes from here to here. So this means, in particular, that it is not it's not possible to write down without making a lot of other choices an equivariant Morse chain complex. You can perturb and try to define it, but you cannot do it from this picture. And so anyway, so this has been kind of a technical problem, technical issue in more than one area. And last year, Simon Reshikov observed something very nice from my point of view, which is that somehow, if you think correctly about equivariant Mordism, this is not a problem. Okay? That this is some problem that arises because we insist on doing things with homology. That if we work in Mordism, and if our notion of Mordism, manifold Mordism is sufficiently flexible, then there's some canonical object that you can associate to this and do equivariant stable homotopy with it from this point of view. Okay? So I won't go into the details, but roughly speaking, he essentially generalized our notion to some notion of equivariant flow categories and keeping track with group actions, and that his notion of equivariant flow categories kind of recovers the category of equivariant spectra, and from it you can recover invariants such as the fixed ones. So there's one new insight. The new insight is that this this moduli space of gradient trajectories that go from here to here that should have the wrong dimension, you should think of it not just as a manifold, but actually as something virtual, or something that we say in these words, derived. It's like a manifold together with a vector bundle on it, and you want to cut out the zero locus, but the zero locus cannot be cut out transversely, so you just keep that additional information. Okay? And that's this formalism sorry, what is it again? Proper derived manifold. So that's the way you formulate it. So now we have some way of understanding the homotopy theory that we can extract out of Morse theory, not just in the standard setting, but also in the equivariant setting. Okay, and then the last thing that I want to end with is that there are still a lot of mysteries in Morse theory, as far as I'm concerned. And I think, to me, the fundamental one that I don't understand is that right now everything that I've said is about constructing stable homotopy invariants of manifolds out of their Morse theory. But that's not the only kind of stable information there is. Okay? So in the 70s, Walthouse formulated the notion basically of stable differential topology. Okay? So this is related to his work on K theory of spaces. He built some kind of Whitehead space, Whitehead spectrum, which refines the notion of the Whitehead group, which refines the notion of stability. And my expectation, my belief, is that if we are there is some way of remembering more information about these manifolds so that we can have this refined information. And there is some indication that this is possible. I indicated, when Smale did with Whitehead torsion, what Abouzaid did with the high-Reitmeister torsion, and also recently I've had some paper with Cook and Guillermo and Krag, where we managed to relate stable Morse theory to the kind of spaces that Walthouse is. But right now, we can only do this in a very concrete way, that is kind of where we study natural functions, cross with R. We don't have an abstract way of doing it, and you say, why would you want such an abstract way of doing it? Because, in the back of my mind, I'm studying symplectic topology, and in symplectic topology, we don't have access to a smooth manifold in which we're doing Morse theory. Everything is taking place on some infinite dimensional space, and I believe that these invariants are still there, but we cannot point out directly what they are. Okay, well that's the end of my lecture, and maybe we have another 100 years.
Any questions from Mohammed?
This is related kind of to the last slide.
Okay.
Maybe old perspective on Morse theory, like you said here with Smale and the Whitehead, where it seems that the simple homotopy type, and then you're talking to them about the stable homotopy type, which is weaker. What's the
So I don't think you should think of it. So one way that in stable homotopy theory one can remember the fundamental group is to do somehow stable homotopy theory over B pi 1. So you take your manifold and you say it has a map to the classifying space, and then you just do things parametrically over the classifying space, and in that way you remember the fundamental. So that doesn't worry me. This thing about pi 1 doesn't worry me too much. We can just build it in the formalism as an additional structure.
Okay. And with that included and everything, does Morse theory just say the homotopy type, or how much of the...
Well, this is exactly what I'm saying here. So what we currently can extract out of Morse theory is stable homotopy type with some kind of information about pi 1 acting on it. But I believe that there is more information about pure differential topology that can be extracted from it. And this is related, so for example, Waldhausen kind of built this theory in part to say something non-trivial about the diffeomorphism groups of a disk. And he said something non-trivial about it. He didn't say everything, but he had some stable range where he could compute non-trivial homology groups of the space of this out of the machinery of algebraic K. But if you, and I encourage everybody to do so, even though it's quite a task, if you go try to read Waldhausen's manifold approach to K theory paper, I mean to A theory paper is what he called it. Okay? There he explains how he's working with some kind of differential topological notions. Okay? And those differential topological notions do not currently have any Morse theoretic interpretation. And if we had it, then I believe we would be able to apply them more generally, including symplectic topology.
So is your belief Morse theory, like everything smooth topology, should have a Morse theory?
No, that is not what I said. I think what I want to say is stable phenomena.
Okay. Thank you. Yeah, Jake.
I have a question about this general approach of doing Floer theory without spectrum, basically, like staying on the flow canvas
Yes,
and
yes,
it's very
yes,
fascinating. Like while I understand the intuition of like the passage is too cumbersome, stable homotopy theory is one of the fields that's like extremely. We have very useful computational tools.
Yes,
Like it's
I want to use them.
it has a very deep theory. So without passing to stable homotopy theory, are you not kind of like, is it that a shortcoming of this?
So let's think about it like this. Let's say that you try to construct an E-infinity ring spectrum on this side. You know you have to build a whole lot of coherent data. How are you going to do it? Okay. But the coherence data aren't here. So what you should do is formulate the E-infinity ring spectrum here, okay? And then show that that notion is the same as there. So this is what I mean by the structure should be built on this side. They should be understood on this side. Once they're understood on this side, the ones on the other side usually have universal properties anyway. So then you can just use them. But you should build them here. Because it's too hard to build to say, I'm going to build all the coherences of an infinity ring spectrum by taking my huge collection of manifolds with corners, apply Pontryagin-Tom to each of them, and check that I could have done it coherently so that I have all the relations that I want. That's one example. The other example that I like to give, the paper is not out yet, is that for about 20 years, probably more so, people in stable homotopy theory have been saying, what are these curved algebras that you have? How, but of course, I'm saying we can just define them this. And you can define them over the sphere spectrum. It doesn't matter. So some things are clear, and just try to translate them. Sometimes they're less clear. Sometimes it's obvious what the translation is, but you still would have to do it on this side anyway.
Any other questions?